Bismillahirrahmanirrahim. Assalamualaikum. Terima kasih kerana sudi hadir semua hari Ahad ni, sanggup meluangkan masa. Jadi hari ni saya bercakap dengan orang daripada kumpulan graph theory. Jadi mungkin saya akan tersasul-sasul sikit sebut network atau graph, tetapi saya nak terangkanlah bahawa sebenarnya pada saya, at least cara saya berfikir, network ni walaupun kadang-kadang saya guna perkataan link atau node, tetapi mathematically memang dia adalah graph lah kan. Vertices atau edges. Jadi untuk graph theory punya group ni, saya rasa semua panggil G adalah graph, V adalah vertices dan E adalah edges kan, macam tu. Tapi notation ni sama juga kita guna dalam network. Cuma nama je dia dipanggil lain-lain. V ni dipanggil link, dia panggil node, E ni dipanggil link, G ni dipanggil network. Ya? Okay, kalau ada soalan boleh tanya. Cuma saya nak maklumkan ada banyak cara lah. Jadi sebab dalam computer science banyak digunakan perkataan network untuk mewakili objek ni. Objek yang bentuk sebegini kat tepi macam ni kan, yang bulat ni dipanggil vertices atau nodes, dan garisan tu dipanggil link atau edges. Oh sekejap, saya lupa nak tanya, semua orang Malaysia ke? Is there any foreigner joining? Should I use English?
Aisyah, tolong semak Aisyah.
Kejap Doktor.
Maybe I should use English just in case. If let me know if I can change back to Malay or whichever one you prefer. So what are networks? Networks can be vertices or edges. In mathematics it's called a graph. In computer science it's called networks. In physics it's called site or bonds, but in theoretical physics usually we call it network as well. Okay. And then in social science, sociology and social network analysis, we also call it network, but sometimes in sociology, we also call it actors, ties, and relation. So I just want to highlight that we are actually using different terminology and different words to depict the same object. So if you see me sometimes slipping into pronouncing the vertices as nodes or the edges as links, forgive me. I will try to refer as vertices and edges as people in graph theory are used to. Okay. So that's the disclaimer. So let me start the story. So if you want to watch the video later, this is just a 1 minute video. But the first part of my talk will be about networks of COVID-19 spreading. So if you can visualize that this is a contact network of potential people that one of them was infected with COVID, and how would the disease spread along the network. Okay, so that is the core of the first part of my presentation. All right, okay. So the network effect is very important in spreading COVID-19 because I think you might have seen this image. It is by Professor Sisiu, I think, from New Zealand. So she created this image in order to make people understand how dangerous it is if you went to the barbecue or flew on an airplane, or you stayed home. You might save all these other people here from being infected, and then these people work from home, you save all these people here from being infected. So the network effect is very, very important, especially in epidemic spreading. Okay, so if you want to just get a basic idea of who is the super spreader in very simple terms. I think this is also used in graph theory. You use the measure degree, right? You use the measure degree to count the number of edges. So for example, I have degree 2 here. This is Datuk Nora. She works at Maybank. So her degree is 1, 2, 3, 4, 5. And then this is Marwan. He is from IIUM. So it's degree 1, Fiza has degree 1, Iza has degree 1, and Suri here has degree 2. So in this sense, Datuk Nora is the super spreader because she has the highest degree. And also, also important degree in this larger network here when you have a high degree centrality. Okay, so I have to explain the term centrality. Don't worry, maybe in graph theory you don't use the term centrality so much, but centrality is just to measure importance, I would say. How important it is, to measure importance. Yeah, okay. So centrality, if you use degree to measure importance, you call it degree centrality. So in this case, J has highest degree centrality, but H has the highest betweenness centrality. So betweenness centrality measures how much the vertex connects one vertex to another. So in this case, humans can see that this is almost like, oh, sorry, kenapa dia jadi macam tu? I see. Okay. You can see humans can quickly see that this is divided into 2 clusters. So we can see that without H, this cluster and this cluster would be completely separated. So if M is infected, for example, it won't spread to this cluster. So the super spreaders can also be people with high betweenness centrality or high closeness centrality. Closeness centrality, very simply, is closeness centrality is you measure the distance, and then you take the inverse of the distance, meaning it's a ranking of how close the vertex is to every other vertex in the networks. And eigenvector centrality, very simply, is just a generalization of degree centrality. For degree, you count how many edges a vertex has, but for eigenvector centrality, you don't only take into account your neighbor's edges, but you also take into account your neighbor's edges, and you take into account your neighbor's edges, and then it's actually up to infinity, and then you can derive a formula that shows that the eigenvector centrality is the limit to infinity. Okay, so that's a very simple overview of the centrality and who we shall consider as super spreaders. So basically in my paper, I tested the degree, the betweenness centrality, the closeness centrality. I actually also tested the eigenvector centrality, but it didn't work very well on my network, so I didn't put it in the paper. But centralities are very important. And also who likes to cluster, as I highlighted before this. Humans can see 2 clusters just from looking at the network or the graph here in this sense. Like here, you can see clearly where is the cluster. The cluster occurs between me, Suri, and Datuk Nora. And that is the definition of clustering coefficient, where you count the triangle per all the possible triangles in the network. Very simply, if you need to count the clustering coefficient of a network or a graph, you just count the number of triangle per all the possibility that the triangle will occur in the network. Let's see. So we can also calculate the local clustering coefficient. So I think D might have the highest clustering coefficient because it has the most triangle around it. 1, 2, 3, 4, 5, 6, I think. Yeah. So very simply, centrality is a measure of importance, and clustering is counting how there are local measure of clustering where you can calculate the clustering coefficient for each vertex, and then there's the global measure of clustering where you can just calculate the triangle per all possibility of triangles, or some other people define it differently, that they take the average of the local clustering to get the global clustering of the whole graph or the whole network. So that is very simple, but if you want to know more, you can ask me. Clustering coefficient. So how does social distancing leads to the flattening of the curve was the question I asked myself during Corona when I was looking at my students' data, and I was reading all the material because I wanted to understand. So this is the figure where you see in the newspaper or anything like that, that you have to delay the epidemic by reducing the height of the epidemic peak, which is this graph represent the number of infection, right? Okay, but okay, how does the contact between human lead to this number of infection was the question I asked myself. And so we look at the very general famous mathematical model of epidemic disease, and the most used model arguably is the susceptible infected recovered model, SIR model. So in the SIR model, it is assumed that we have like a group of susceptible people and a group of infected people and then a group of recovered people, and these people and this is the simplest model. There are many versions. So these people say that S infects I with probability beta, and I becomes recovered or removed actually. So it's either you get cured or you, na'udzubillah min zalik, die with probability gamma. Okay, so that's a very simple, susceptible, infected, recovered explanation. And there's a different set of beautiful differential equation that can get this kind of graph. This not the object graph, XY graph. Okay. Okay, but then one can ask that, you know, in real world, people are not separated by susceptible, infected or recovered, because we are all mixed, you know, like an infected person can be next to a recovered person, but it can also be next to a susceptible person and infect this susceptible person. Okay, so because in real life we know that we actually mix together like this, it becomes the contact network underlying the mixing would be very important in determining the spread. Okay, so it also lends very nicely to explain contact tracing and isolation, and why contact tracing is very important. And when you isolate certain vertices from the network or from the graph, it's very efficient in curbing the spread. And also it's very convenient for explaining why infection clusters are very important and super spreader events are very fatal. Na'udzubillah min zalik. Okay. Okay, so in my latest paper, like I said, I was looking at my student data, the networks gathered from my student. So this is one. Say this is one student and this is another student. So the vertices are students, student 1 until student 141. And then the edges are friendship between the students. Well, wouldn't say set. Friendships between the students. So how did I get the friendship between the students? I asked them, we made it compulsory for them to ask a questionnaire, and then they answered the student. But this paper, which I wrote in Malaysia now, is not actually about this questionnaire, because I already published this questionnaire in another paper, which I will show you later. But I was looking to understand other issues related to the students. However, due to COVID-19, because I wanted to know how the spreading happened, I modeled the possible infection spread on the network using the SIR model on the network. So the SIR model on the network is not the very nice differential equation that people usually use, because that type of SIR model assumes a homogeneous mixing, meaning everybody meets everyone. But on the network, you only meet the one you are connected to using through the edges, right? So for example, this person, say this is student 1, only talks to student 2, student 3, and student 4. It doesn't meet with other students. So in terms of disease spreading, you can assume that 1 can only spread to 2, 3, and 4 with a certain probability. So what I did to model the spread of epidemic on the real networks of student friendship is that I model the SIR using the Markov chain Monte Carlo model, meaning that you just say that one time step depends on another with a certain probability. Okay, more details in the paper. If you want to know more, let me know. Okay, so this is the results. For example, this is the result of one time step, where you can see here the infection peak at time 13, which is showed here. The network is this is the network for time 13 is displayed here. So you have the maximum number of infected person at this time. So you can see most of the network is red, so meaning most of the students, the simulated students, not the real students, are infected. Thankfully, the students are at home. Okay. And then, so from this, we can see that we can understand the spread of epidemic on the network in this sense, using the Markov chain Monte Carlo. And then what we did was, okay, how do we want to, if we want to open the university again safely, what can we do? If we know the contact network given by the friendship network, or maybe in future, we can actually ask the student to tell us out their contact network, or we can have this has actually been done by other educational researchers. They ask their students to have like a tag on their phone, so they can like detect if they come close to another student, so with a certain proximity. I don't know, I think with current technology we can do this. There's a technology where you can detect if you come like how many meters closer to a person. Your phone, maybe like a My Sejahtera app or something, can detect that you are close to this person. So if a company or a school really wants to open safely, and they have their workers wear this tag or detector, for example, or they make their students or the workers of the company meet only they limit their students or their workers to only meeting certain individuals, so they can control the spread of COVID-19 in an ideal situation. Obviously, there's going to be an exception, but we can only do what we can. Okay, so this random monitoring, what does this mean? Meaning that in the paper, there was a spreading process on the network, and then we simulated the case. What will happen if we randomly monitor 1% of the students, meaning 1% of 148 students is 1.4 students. So we monitored 2%. We round it up. Okay, we monitored 2 students, sorry. Okay, so 1% monitoring is 2 students. So 10% monitoring is 15 students. So what we did was that, meaning this, so this is a simulation of the testing process. For example, if you test a student from time to time, test positive COVID or not. So if you just test randomly, that is what we call random monitoring. And then at each time step, we assume that a random person will be tested. So for this simulation, the monitor 1% is that what we did was that we we randomly tested 2 students at each time step here. So there's 100 time steps, so representing days. Okay, so we assume that we test the student, 2 students every day. And for 10%, we assume we test 15 students every day, and 20%, 30 students every day. So you can see that by testing, you can catch when these students are infected very quickly. So that's why this is the normal curve. So when you monitor just 1%, you can reduce the peak of the curve. And 2%, 3%, 4%, 5%, 10%, and 20%, it's less than 5 students were infected if you randomly monitor. And then quarantine. So by quarantine, what we mean is that we separate the vertex from the graph. We just take the vertex out. Basically, we make them unable to infect other people. Okay. So if you monitor by degree, this is what happens. When we say monitor by degree, what we mean by monitoring by degree is that we measure the degree of the network, and then we take the 1% of the highest degree. So meaning this is 2 students with highest degree. Degree centrality, or just degree is the same because normalized sometimes for degree centrality. But 2 students with the highest degree will be monitored. It's reduced quite a bit more, I think, than the randomly testing 2 students. And then when it's 20, it's not only the peak of infection is reduced, but also the time is shifted. And this is like the flattening of the curve that everybody wants. You know, you delay the peak and then you reduce the peak as well. Okay, so it peaks at 12% only at time 23, and then before that it was peaking at 5%. So it's not as good but it is the peak is delayed later. Okay. But the better result is what happens when you monitor by betweenness centrality. What happens here is that you see that it goes down faster when you monitor just 1% here. It's already 62% by 12, meaning you test 2 highest between centrality students here every day. Meaning before this, in the random testing, you tested different different student every day. But because you already know the network or the graph, you target these 2 high degree or high betweenness centrality individuals, and you test them every day rather than you test everybody else. Okay, so this is what we simulated here. And then when we do that, we see that the reduction becomes really clear when you monitor just 10%, it goes to 8. And then 20%, it's almost completely flattened. And this peak 1% is because the simulation says 1% has to be infected at the very beginning. So that but yeah, so this is essentially flat. So we can say that between centrality is very effective to use to reduce the peak and the time of infection as well. So that was the result in our paper in Malaysian. Okay, but other than just disease spreading, we wanted to highlight that actually, okay, underlying the network, we have susceptible, infected, recovered. This is their status or their state, as we call it in statistical mechanics. But there are other socio-economic underlying factors as well. Because, for example, these are the races or ethnicity of the students, and the circle is the female and the squares are the male. Okay, so boys and girls. So you have gender, you have ethnicity, you have income, you have state of origin. So there's a lot more information underneath the network or the graph, which initially I was trying to analyze, but then suddenly COVID-19 came and I thought, well, Science Malaysia now has a special issue. Let's do a modeling of epidemic spreading. But yeah, I just wanted to highlight that we are working on this, and hopefully we'll get to compare and contrast all this. So if you have a graph, a real graph, there are so many underlying considerations to take into account, and not just what ethnicity and variables on the different vertices. The same vertices can also have different edges depending on what you choose to define as the edges. For example, okay, so this is the paper that initially what we did was we used it to understand student mentoring network. So different links, that's why links are edges here. Okay, so this is directed edges. So this is the same node but different edges, and now the edges are directed. As you can see, it's not completely connected because this student doesn't mentor anyone. These two students just talk to each other, just mentor each other, and all the other students are connected somehow, even though some are like barely connected at the end. And so we, for the same students, we mapped it to different, using a different edges. So if you want to, if anyone from graph theory wants to use real network, and I think some of you have, there's a lot of aspects that you can look at. You can try out different edges, you can try out directed, undirected, weighted, unweighted, many different measures, degree, centrality, and then you can put many colors, and then you can put the sizes according to the weights, and I'm sure people in graph theory already do this, but I just wanted to highlight an example of it, some of the things that I did. Okay, so yeah, let me see the time. I just wanted to highlight that there are so many models, and so what can we rely on? So for me, after doing some reading, I prefer a data-driven population model. One of the most famous model was from the Imperial College, Neil Ferguson team. Reported to change Boris Johnson's mind, the Prime Minister. Before that, he said that he didn't want to close down UK, but after seeing this graph is actually really scary if you look at it. That, you know, the search capacity is actually this red line here, and if you do nothing, it will go way beyond the search capacity. So because this graph was really scary, that's why the government of the United Kingdom reportedly closed down their country. And it's a good thing Boris Johnson did that before he got COVID himself. Otherwise, it would have been worse for him. And then another model, GLIM, by Alessandro Vespinani. He is from the Network Science Institute at Northeastern University in the Cambridge area of the US, Massachusetts. So his team, very quite famous even before the COVID pandemic. We in network science is really famous for network epidemiology, which is what I essentially did showed you before. You model the epidemic spreading on the network, and from their modeling, worldwide modeling, very basic estimate of international travel, they estimated that the Wuhan quarantine reduced international transmission by 80%, meaning it was effective to reduce the transmission for a certain time, but eventually it reached us. Okay. So flattening the curve, so the picture that you actually see in the papers or everywhere that tells you to flatten the curve is actually from this Imperial College estimation. Well, not just from them, but most famously it's probably from their estimation. That is highly cited, and usually when you talk about corona, usually this paper will be referred to. And so now you know that the flattening of the curve is actually, so this is just a cartoon, you can say, or a toy example of the actual graphs where people plot the infections, generally using a variety of the SIR or SEIR model applied differently, not just using the differential equation, but also using Markov chain or other methods such as agent-based modeling. Okay, so that was the end of the first part of my presentation. There are a few points that I would like to highlight, and maybe I would like some feedback from the audience if you have any question before I move on. First is that usually measures utilized in network analysis have very intuitive explanation. So if you want to introduce a new measure in network analysis, for example, you need to have like the intuitive explanation backing the measure, and then usually you need to show it on real data sets, or at least different types of graphs, like the complete graph or the random graph or the scale-free graph or the small world graph that shows that it can be utilized in real networks. Okay, that's the first point. The second point, networks or graphs can be defined in many ways and has underlying information such as ethnicity, gender, income, and also can be connected in various ways. And the third one, oh sorry, I misspell new, not any news measure, any new measure. Any new measures in graph theory that can be applied to solve problem in real networks. I am very interested to hear from your community, and if you have any suggestions, I think we'll take a break. Is that okay?
Okay, Doctor. Alright, so actually there is a question from the chat box here, Doctor. From Dr. Roslan. Okay, so Dr. Roslan asked about what is the best measure in social network analysis among the three measures, which are individual, intermediate, and group. So which one is the best measure?
Dr. Roslan, can you explain what are the intermediate measures?
Tapi masalahnya Dr. Roslan dah left.
Macam tu tak berguna jugalah jawab kan? Okay, alright. Well, maybe saya boleh komen sikit lah. Kalau dari segi saya punya bidang yang saya buat PhD dulu, you have the micro, meso and macro, right? So maybe intermediate measures tu dia masukkan macam meso punya measures lah. Mungkin macam kalau dari segi network tu dia masukkan mungkin community detection ke ataupun cluster ke. So kalau micro tu individual tu dia ada ranking kan untuk setiap business centrality setiap degree. Tapi kalau untuk intermediate tu mungkin apa yang Dr. Ruslan masukkan tu adalah macam kalau kita measure untuk satu kumpulan tu ada entropi dia ke, entropi tu satu benda lain pula, ataupun dia punya clustering coefficient ataupun yang entropi tu mengukur kepelbagaian dia. Tak ada foreigner kan Aisyah?
Kalau saya tengok nama semuanya okey.
Okey.
Cuma
okay. So saya cuma takut ada foreigner. Itu satu jawapan lah kot. Mungkin Dr. Roslan nanti tengok rakaman lah agaknya.
Okey, Dr.
Roslan ada meeting Dr. Fatimah.
Apa dia?
Dia masuk sekejap je. Dr. Roslan ada meeting, dia masuk sekejap je.
Okey. Tapi kalau apa soalan dia tadi terbaik mana yang terbaik?
Which one the best?
Sebenarnya saya rasa kalau dari segi mentality statistical mechanics atau statistical physics, yang terbaik adalah sekiranya ketiga-tiga tu boleh dihubungkan. Sebab kalau secara amnya kan masalah besar dalam fizik adalah ukuran di antara planet-planet tu tak sama dengan quantum mechanics. So the quantum mechanics, the probability apa semua tu lain. Dia tak sama. When you look at the bila tengok atom dan zarah tu, dia punya probability dah lain daripada hubungan di antara planet-planet. So ukuran yang terbaik bukan untuk mana-mana level, ukuran yang terbaik sekiranya ketiga-tiga level tu micro, meso dengan mikro, maksudnya individual, berkumpulan dan keseluruhan dapat dihubungkan dengan probability yang jelas ataupun equation yang jelas. Kalau dapat dihubungkan itu yang paling baik lah.
Okay, Dr. Okay, jadi is there any question anymore for Dr. Fatimah? Ada sebarang soalan lagi kepada Dr. Fatimah?
Doktor, saya Zuri.
Hai Zuri.
Untuk yang micro, meso dan makro tu, saya nak tambah boleh ke?
Boleh ni. Zuri ni perkenalkanlah diri dulu.
Oh yeah, hi everyone. So I think I need to speak in English. I'm a PhD candidate with Dr. Fatimah and I'm working on real-time financial networks. And the question from Dr. Roslan, I honestly think there's no, it doesn't work like that, like which one is the best, they work together. And they are measuring different things. Micro is micro, the individual knot. Meso is the in-between knots. And macro is the systematic view of the network itself. So I don't really, personally from me, I don't really think one is the better one. They have different measures. But that's my opinion. That's it. I just want to say that. Thank you.
Alright, thank you, Mr. Zuri. Okay, so is there any question anymore? Ada yang lain nak bagi soalan kepada Dr. Fatimah?
Okay, kalau tak ada, saya sambunglah kot.
Okay, Dr.
Alright. Okay, thank you for the question. Boleh nampak ke?
Okay, Doktor, nampak.
Alright. Saya nak hide Dr. Stop sharing pula. Sorry. Minta maaf. Okay, so sambung lagi cakap tentang bahagian kedua lah, financial network. So bagus juga Zuhri dah bersuara tadi. So siapa nak dengar suara dia lagi, bolehlah tengok video ni, Not Network Science in Industry, ada dekat YouTube. Dia dah bagi a whole talk tentang kenapa network science ni penting daripada perspektif dia semasa dia dah bekerja di industri lah. Okay. Thank you Zuri. Jadi saya nak cerita sikit lah saya punya pengalaman masa saya buat attachment 6 bulan dekat Maybank berkaitan dengan financial network. So yang ni sebenarnya fellow-fellow daripada universiti-universiti yang buat attachment dekat Maybank lah. Padahal bidang-bidang mereka semua berbeza lah. Ini Fiza ni virologist, Marwan ni ekonomis, and Izzat ni lagi lah nanotechnologist, kuliah pharmacy, IUM. Jadi sangat berbeza, tapi mereka semua mengatakan bahawa sebenarnya boleh apply network dalam bidang mereka. So saya dah pernah bagi talk dekat dia ni punya student, dia punya department, Marwan je belum lagi. Tak apa, itu kena test lah. Dan of course dekat Maybank ni pun saya memang bagi talk dekat group Datuk Nora ni. Dia adalah kumpulan Human Capital Development. So she is the Chief Human Capital Officer, CHCO. So dia dalam C-suite, she is the top management of Maybank lah. She is the top management for Maybank worldwide in terms of human capital, meaning she is the boss of HR. So I was explaining to her how human relationships are very important in terms of networks and how you can manage your team using a network point of view. But that one, we can talk about it later. I want to talk about the financial transaction first. So what I described to Maybank is that if you have data of financial transaction, and of course they do, but so for example, you can monitor who transfer money to whom. So for example, A transfers money to B, and then B transfer money to C, and then the links, the directed links or the directed edges, the financial transaction conducted through Maybank, right? So because Maybank is the biggest bank in Malaysia, they would have a lot of information, and by identifying who has the maybe a highest degree, highest between centrality, they can identify who are the most important maybe company or maybe institution that is keeping the network, the financial network together, financial transaction network together. For example, if you want to know which SME is the most important and should be given most support during COVID. So maybe this SME, whatever H is, if this SME goes bankrupt, then the network would be completely disconnected, meaning this group won't be connected to this group in terms of maybe the supply chain, for example, or whatever financial transaction, whatever the financial transaction was about. So that was how I describe networks to Maybank, and I did some network analysis, but I cannot talk about it here because of the privacy and confidentiality. But this idea is not new and is well known, but I'm just putting it out there. So if you have this type of transaction data, you should model it using this kind of network approach. And then so one example of credit card network of financial transaction in 2011, it was the card issued by UAE in 2009 by HSBC through Visa. Yeah, it has Islamic banking. But why do we have this figure? Because it was exhibited in the British Museum as the history of the world in 100 objects. So the object was a credit card. Okay, so the interesting thing is the credit card network. So this is the amount of money transferred. I think that's why the weight is biggest, but they didn't really give too much detail, and they highlighted the worrying transaction over here. Honestly, I'm not very sure how they quantified worrying, but this is just a nice visual. So if you have the data, for example, the transaction, so maybe you say because Italy is really small, but the transaction is so big, like this almost the same amount as United States transaction, then it's worrying. Possibly you can also, from using a general point of view, just really detect which one is the problematic country. So we did see later that there was a lot of concern about the economy of Greece, Italy, and these ones that were highlighted. Okay, that's one view of the financial network. Okay. Next, because we don't have actual financial transaction data, the next best thing that you can do is you take the time series you get from the stock market. So this is an example of the data that I got from this website. Nothing special, I just got it from this website, but this is a graph of citations from bioarchives or archive or Peergy. They're all preprints, right? Okay, so citation per month, I think. So for example, if you want to connect, let me label this B, this one is A, this is our archive, and this one is J, pure J, B, A, J. How would you connect if you have a node B, a node A, and a node J? How would you connect these node or these vertices, right? Okay, so one very popular way is that you would take the correlation between these time series. So you will take the correlation between B and A, for example, and if the correlation is high, above a certain threshold, which you would have to determine yourself, then you say, oh, okay, B and A is correlated. But from here, you can see clearly that B and A does not look very similar. So the correlation value wouldn't be very high, but A and J is quite similar, well, relatively similar compared to A and B or J and B. So you can use the correlation or Spearman correlation. Sorry, not Spearman, Pearson correlation. Pearson correlation. You can also use Spearman, but usually we use Pearson, and Spearman is for the rank case, I think. Okay, so then you will get like a connected or disconnected network from these BAJ. So in this sense, from this network visualization, you can say that the PJ is connected to the archive, archives here, and not connected to the bioarchives. I don't even know how to pronounce it. Bioarchive. Okay, so you get a graph from this one. But what we usually do in analyzing the stocks, there's much more than 3. Usually we play to around hundreds, but there are way more stocks than that. Okay, but Pearson correlation is not the only way that we can use to measure the similarities between A and J, B and J, and A and B. So one way to measure how similar it is, we use the correlation. But another way, which in my opinion captures a slightly different or more complete than correlation, because, for example, if you okay, mathematically, we know that this is the definition of independence. Probabilistically, if two variables, x and y, are independent, then their marginal probability is their joint probability is the same as their multiplied marginal probability here. Okay, so this is independence. However, the correlation, which the Pearson correlation, which I mentioned just now. So, for example, if you say that correlation is symbol modeled by this symbol, and then XY, when it's equal to 0, you get this probability. When the Pearson correlation is equal to 0, you get this probability. But this is not the definition of independence, but it is the definition of linear independence only. So you get sort of an approximation of independence from correlation, but it's linear and it's not as complete as this definition of independence. Okay, so correlation coefficient, okay, so all right, I used this symbol just now. Yeah, ignore this. Covariance is just correlation without division by standard deviation. But the correlation coefficient here, this is the full equation. When this correlation coefficient is equal to 0, we get linear dependence. So this is the normal correlation coefficient that everyone learned in their degree, I hope. And so what our group is using, we are using mutual information based on Shannon entropy. Don't worry about the H, but what I wanted to highlight is just here. Because when Shannon entropy is 0, you will get that this equation is equal to this this ratio is equal to 1, because log 1 is equal to 0, right? Okay, so this equation will equal to 1. So then you get general independence, which implies that Pxy is equal to Py. Okay, Pxy there. So you get, so when mutual information is 0, you get complete independence, but when correlation or covariance is equal to 0, you only get linear independence. In fact, in this proceeding, I put I highlighted an analytical example of a case when correlation is equal to 0, but mutual information is not, when we use centered random variable. And I don't think anyone else has ever given an example of this case. So I think so far for now, I am the only one who I know of that has given an example of a case where the correlation is 0 and mutual information is not. So usually what I say why this is important is because it's suitable for complex system, like the financial market, for example, which is like super complex with non-linearity. And we might miss some of the non-linearity if we only use the correlation coefficient, even though I have to say that correlation coefficient is quite reliable. And if you are if you just want a quick calculation, I would recommend correlation. Okay. And then that's one level, dependency and linear and non-linear dependency. So my main point here is that in order to build a real networks or graph from time series data, you need to find a similarity measure between the various time series that you have. And there are different types of similarity measures, correlation, mutual information, and the like. But there is also a type of similarity measure that has direction as well. These ones also, you have linear and non-linear directed similarity measures, or you can say it's sort of a causal indicator. Okay, so the Wiener-Granger framework of Y causes X. So first, if you predict the current value of X using the historical value of X, and then you do another prediction where historical value of Y and X are both used to predict the current value of X, you compare the former to the latter, and if the second one, number 2, is judged to be better than the first one, then you can conclude that Y causes X. So okay, this is too wordy, but let me just show you what I mean by this. So this is mutual information, which I explained briefly just now. You like this part because when mutual information is 0, then you get log 1 and you get this general independence. So what transfer entropy does is it just add here, it just add X here, time shifted X, and also yeah, actually you can show that this is also by factoring out, you can get the conditional probability. You replace it here, and then you have 2 time shifts of X plus 1 and X. So basically you use the information from X in time n and Y in time n to predict the value in time X n plus 1. Okay, that's just the idea. If you want to know more, you can ask me. But basically, what I wanted to just show in a very general manner is that we can get a directed graph from using this method. You can use Granger causality, which is, to my knowledge, a linear directed method, or transfer entropy, which is a non-linear directed method, to get a directed network from financial time series and any time series, actually, meteorological or any type of time series, you can get it, and then you can get a directed graph. Yeah, so for example, if anyone from graph theory is interested to analyze the time series that you have, this is one way to get a directed graph. Or if you don't want the direction, just want to keep it simple, just use the correlation. Okay, so if you are interested in this one, you can watch the Hasanuddin, my PhD student's presentation at SKSM 2021, and this is the proceeding if you want to check it out. I think from the result, you got that Borneo oil berhad is the stock that is here, most influencing other stocks when measured by in degree and out degree. So I think everybody knows, but in degree is when the arrow is pointing to you, and out degree is when the arrow is pointing towards somebody else. Okay, so here is a simplified network. So initially what Hasanuddin plotted is 480 Sharia stock, but then because he took the threshold, I think, higher, so some of the stocks weren't connected. So this is probably just the giant component of the graph that he is highlighting here. So this is the time series line is 776 trading days. Okay, so basically that's all I wanted to say about financial network. Is there any questions? Is there any questions from anyone?
Okay, Dr. Fatima. Okay, I have a question.
Yes.
Okay, since you are using what you call knowledge about the graph theory in the network, right? You are using graph theory knowledge inside the network. For example, like a degree. And then another one is how you interpret the graph. That one is using from the graph theory, right? So
Yes.
other than degree, so is there any properties that you use in this network? Meaning how you we not generalize, but we identify or we research the network by using other properties of graph theory. For example, maybe about coloring. Is there any possible way to do in the network?
Coloring not so much because I'm not sure whether I'm right, but do you need the graph to be planar for coloring?
Planar?
Mm-hmm.
No need, no need.
No need, right?
No need. But I think it's just
Dia Dr. Fatimah,
yeah.
vertex yang bersebelahan tidak boleh di-color dengan warna yang sama.
Betul. Tapi
Ataupun kalau kita ambil edges pun boleh juga.
Betul. Vertex coloring dengan edge coloring kan. Sebabnya saya punya pengalaman lah, dalam real network macam tak ada reason sangat nak cari edge coloring or vertex coloring. Saya pernah tengok application tapi macam application yang tak boleh nak publish paper lah kiranya. Macam not solving the problem. Macam tu. So kan dalam network ni the most important thing is what problem do you want to solve, right? Not whether the application is mathematically fun or not. Saya tahu graph coloring ni memang fun. Saya suka kan yang peta-peta tu semua kan. Tapi dia memang penting lah in its own right. Kita tahulah macam mana nak separate tu. Tapi application wise mungkin saya yang tak nampak tak ada sangat. Mungkin ada satu dua lah yang nak bahagikan kumpulan pelajar ke supaya tak sama kan dengan yang lain. Once you have this attribute, you don't want this student to be in the same group. That might be one application, yeah. We can do that. Kalau if you feel that, okay, I have these student networks, right? So I don't want them from the same state, for example, to be in the same group, then maybe we can use graph coloring. That's not a bad idea. Yeah.
Okay, Doctor. Thank you.
How do we choose the highest betweenness centrality among the nodes in the network? There's a formula for betweenness centrality. Let me explain it very simply. You need to find all the shortest path in the network between each and every vertex, and then count whether that vertex is in the path between these other two networks. Between these other two vertices. Very simply lah. But you can refer to my paper if you want the exact formula, and you can just Google lah di dekat Wikipedia. IU. Yes. But actually I didn't actually show you the formula, but because the calculation is actually quite involved, because you need to actually find the shortest path between all the vertices in the network. I hope that answers your question, Ayu. Anything else?
Okay.
Doctor, a general question for me, is that okay?
Yeah, yes, sure.
We have a lot of terms, graph, network, links, and those sort of things, and it can be quite confusing. Do you think there is even a remote possibility to unify all the terms? Because it's being used by so many fields, although fundamentally it came from graph theory. We know that it's being used by sociologists, physicists.
Actually, if I don't know, but
it's a broad question, by the way. It's okay if there's no answer for it. It's okay.
Yeah, but it's a good point. But it's just because macam orang in graph theory pun tak bercakap sangat dengan bukan tak bercakap sangat. It's just like dalam network science pun, dalam computer science pun ada yang guna graph juga, ada yang guna networks juga. So it's not like a completely homogeneous thing. So ideally you would want to throw out the jargon so that everyone can talk to each other easily, right? But I don't really see how because they have like separate conferences, separate society, separate many things. So yeah, I don't know if it's practical lah. And if I say that, I don't know if anyone would listen. That's the answer.
It's still such a huge field. Thank you for the answer.
Okay. Any other questions? I'm sorry if I overwhelm you. I didn't want to scare you from trying to make your own networks of graph, but I hope that you will try, and then maybe some real networks, maybe you have some time series and you can try to get a graph from your time series. No more questions?
I think there is no more question, Doctor. Okay, alright. So thank you, Dr. Fatima.
Aisha, can I iklan sikit? Kalau tak
boleh, no, tak ada masalah, boleh.
Okay, since there are no more questions, I just wanted to tell you that we are having oops, nampak tak?
Okay, nampak.
Okay, so the last time we had WCNTDA 2019, Dr. Sharifah Kartini datang and team UPM datang kan. Tapi yang ni je saya nampak Dr. Yao ada dengan Dr. Chan kat sini kan. Dr. Sharifah was not in the picture. Dr. Hafiza ada kat sini, Dr. Munira ada kat sini. Siapa ada? Sabri ada, Sadiq ada.
Kami ada kat belakang. Saya dengan Dr. Fitri kat belakang. Tak nampak aku.
Okey lah, Dr. Sharifah kat belakang. Okay, so terima kasih sebab datang. So I just wanted to inform you that we are having WCNTDA 2021 special session with Prof. Salmi, Berdekat Bersama Matematik, because it's his birthday on 10 October 2021, 60th birthday. So
by online or face to face?
Online, of course. Online. Semua free saja. Jemput datang. Ada hadiah untuk dia menangi. Grab voucher up to RM80. Grab voucher.
Nanti Fatimah ingatkan semula.
Officially we will sebarkan. But we haven't got the formal kelulusan yet. I'm just so this is the first time I'm letting the public know that we are having this workshop. So this is
birthday Prof. Salmi?
This one, 10 October, yes.
Oh, sama dengan birthday Prof. Isamidin.
Oh, okay. Jemput nanti datang sekali.
Nanti saya maklum pada Prof. Isamidin Rahimah.
Yeah, but this might be in Malay lah. Berdekat Bersama Matematik, because Prof. Sami wants it to be in Malay. But the team, there are other speakers as well. Dr. Afta, Dr. Paul Expert that came last year. And Fariha join kot there. Fariha yang pensyarah USM. They will talk about clustering methods. Some of it will be clustering method statistical, some of it will be on pH, persistent homology or topological data analysis, and some of it will be on networks. So yeah, so that's all I wanted to iklankan. So thank you.